Hello everyone again. So I hope that everyone is able to understand me and can hear me.
Yes, and can you share your screen?
Yes. I try to do it now.
Yes, perfect.
So, okay, so here I hope you can see the title of my talk. So is it okay with the window?
Yes.
So yeah, before I start, I want to thank you very much for giving me the opportunity to give a talk here. I'm also a little bit excited about this. I know that there are some experts in this field here in this seminar I never have met before, but I read some of the papers. And yeah, so it's quite late in the evening. I have over 1 hour for my talk, I heard. So I also prepared a lot of slides and I hope they will be interesting. So I will try to do everything as slowly as possible so that also people can hopefully understand it, which are not experts in this field. And yeah, it starts. So the title is a converse to Noether theorem, and I will now try to explain what it is about. Okay, maybe I have to change this here. Okay, so let me start with some motivation first. So here you can see some of the fundamental equations in physics. So for example, Einstein's field equation, which is written here. Okay, one more question for me. So you can also see my cursor here with the mouse, right? So this works as a pointer, I hope. Can someone say if you can see this movement here?
Yeah. Yes, yes.
Okay, fine. So yeah, so you have Einstein's field equation here. Then you have, for example, Maxwell's equation, and which describes electromagnetic field, and the Einstein field equation describes gravitational force. And for describing some of the particles, you can use Dirac's equation, and then you can couple all of these equations, and then you basically have all the known equations in physics. And yeah, so and these equations all share some property, and they all can be derived by a variational principle. And this is what the talk is about, basically. So for example, for the Einstein's field equation, we have this famous Einstein-Hilbert action functional here. So such an integral functional I always denote by I. And here R is the Ritchie scalar and so on, but this is not so important for the talk. This is just some motivation, and also this equation will not show up later again in the talk. And why does this not work anymore? Okay. Okay, sorry, something. I don't know why this doesn't work. Yeah, so here you have the integral functional for the Maxwell equation and for Dirac's equation. As I said, you can couple them both together and you get this one very long Lagrangian here. And yeah, I already told you that these equations can be derived by such a variational principle, or they can be written as Euler-Lagrange equation. This is the same, it's just a different wording for the same thing. And so from a physics point of view, it would be nice to have some explanation why these equations are all variational. And a possible answer to this question could be that this is because of symmetries and conservation laws, which are also very important in physics. So from a physicist's point of view, it's maybe very hard to explain someone, why this equation, why the physical equation should be variational. But symmetries, I guess everyone has a good understanding what a symmetry is and have some experience in real life. And also for the conservation laws, it's much easier to explain this because we also have experience in this and we know what energy conservation is, for example, and so on. So, and yeah, this is what the talk is about. So with the assumptions of symmetries and conservation laws, we want to prove that some differential equations are variational. So that's it for the motivation part. And I have another kind of motivation slide here, which is this very easy example. So to get into this stuff a little bit more. So let's consider you have a function from R to R. So function u of x depending on the variable x here. Oh, sorry. Yeah, I don't know if the slide something doesn't really work there. Maybe I should try to fix this. Okay, now it works. Okay, so let's consider this very easy differential equation here. So u plus uxx equals 0. So this is, of course, the second derivative of u. And this equation has some symmetry, namely it does not explicitly depend on the x coordinates. So you could also say it's an autonomous system. So, and you can describe the symmetry by applying this partial derivative with respect to x, the kind of symmetry vector field here, and this expression will always vanish also on non-solutions of the differential equation. So this is a symmetry in this case. And we also have a conservation law. So if we multiply our equation expression here by ux, then we can write it as a total derivative of something of this here, 1 over 2, and then u squared plus ux squared. Right? When you differentiate this, then this power 2 cancels with this 1/2 on both of these expressions, and then you get u times ux, and here also ux times uxx. So it's exactly this expression. And when you are on solution of the differential equation, so when this term here vanishes, then of course this whole term vanishes, and then you can easily integrate this expression, and then this thing here must be constant on solutions of the differential equation. And it's, in this case, the energy conservation, but it's not so important what it is exactly. So in the end, the symmetry here and this conservation law, they are also related somehow, what I will explain later, how this relation works. It's of course the relation in Noether's theorem. And yeah, as I said, when we have, let's say, sufficiently many symmetries in conservation laws, then we can prove that something is variational, and this thing here, this equation is variational. So you can, for example, use this Lagrangian here and then compute the Euler-Lagrange expression, and then you get exactly u plus uxx. So your differential equation. So I hope this was understandable. So far, I tried to use very obvious or intuitive notation here. And I will now fix the notation a little bit more. So sorry if the next 3 slides are maybe a little bit boring, but I have to fix the notation. And as you can see here, I will use partial derivatives and total derivatives and so on. And something holds on solutions of the differential equation, something more generally on a jet bundle or so. So, and we need to fix this notation a little bit more, otherwise the talk doesn't make so much sense. So yeah, sorry for the boring part, which is coming now. But I think after this notation part, it's getting more interesting again. So the differential equation or the system of PDEs in my talk will always be denoted by such a function f. And then, of course, here u of x is a solution, and then you have the derivatives of the function u and second derivatives. So I only consider second order systems here, which should be enough for the talk. So yeah, and then I already used this notation here with u. So this is the field or the solution of the PDE. And it can be vector valued. So that's why we have here such an index alpha, which runs from 1 till m. And then we have, of course, the derivatives, which are just here. This DK is a short notation for all of the derivatives here. And yeah, then there is this important thing. So this is the usual jet bundle notation. So there are basically two ways how you can see or how you can investigate a differential equation or a PDE. So you can consider this function u of x as just some variables u, and derivatives, these are also can be considered as just some variables, also with the higher order derivatives here. So then I don't write this u of x, then I just write u when I consider this as a variable. And yeah, we have the x variables where we have this Latin indices I, called the independent coordinates. And then we have the dependent coordinates u. Yeah, dependent because we think of this as a function u of x, that's why it is called dependent. And then we have the derivative coordinates and so on, where we have this index alpha and I. And then I think it's obvious how it generalizes to higher order coordinates here, second order coordinates, and this is basically all we need, so we don't need to go to higher order at this point. Yeah, and then I use this standard jet bundle notation. So we have some base manifold M where the coordinates x live on. And then we have the x and the u coordinates, which are coordinates on the fiber bundle E, and we have this projection here. Basically, we can project down this here to M. And then we have functions u of x, or let's say sections, so which are maps from M to E. And these are special curves. So this curve S satisfies this identity here. So when you project it, then you get the identity on M here. So I guess this is known, but I repeat it. Yeah, and local coordinates for people who haven't seen this before. So a section will just be identified by the function u of x, basically, or by this tuple x and u of x. And then you can compute all of the derivatives of such a section, and then you get this here. And it's called the jet of the section. Yeah, and the same as here, you can consider this as just as some kind of variables on some manifold called the jet space JKE. So all your derivatives and so on are just some additional variables. So yeah, that's already it for the.
I'm sorry, may I ask you a question just to understand what's about your talk?
Yes.
Is it one moment you will formulate statements, something like from these equations, blah blah blah, follows that they are variational. So because I just want to listen to you carefully, can you tell me what will be your final formulations? Something, just give idea. What about will be your statement, just to follow you?
Yeah, the statement will be, so if you have, so I make it very rough. So if you have a PDE and if it satisfies sufficiently many symmetries and corresponding conservation laws, this corresponding, I mean, it's the same connection as in the Noether theorem, then you can prove that your differential equation must be variational.
Thank you. Sorry.
Yeah, so I will formulate this on, I think, on the fourth slide But to formulate it, yeah, I wanted to introduce just this notation because at some point we will need it in the talk, and you know, it doesn't make sense to do the notation at the end. So I know it's a little bit boring at the beginning, but yeah, so let's go through this. So here again, we have this fiber bundle and we have this projection pi. And then we can prolong everything. Then we get this jet bundle, and we can also project down to m if you want with this projection pi k. And we have sections from m to e, so basically identified with the function u of x here. And then we also have sections from m to the jet bundle, jke. And then these are basically, yeah, given when you also add here all the higher derivatives. So maybe the most important notation I want to show you on this slide is that we pull back sometimes the expressions down to m. So for example here, these are just variables on the jet space j to e, and then we pull back it down to m. So everything gets evaluated on this jet here. So you get the function u of x here, and then this whole expression is just a function x. So I mean, it's intuitive, even if you never heard about it. I think it should be somehow clear how to handle such a differential equation. And yeah, and of course, also when we have such an integral functional or Lagrangian, then this will be some differential form, and then we can pull back it here. In this case, with a first order jet. And then we have just here a function depending on x, and then we can integrate it. And omega is some subset on the manifold m or m itself. So dx is just a short notation for the volume form on m. And yeah, omega is some subset of m. Maybe there are some additional properties which are not important at this point. Maybe that the closure is compact or so, but that's not important for the moment. So basically this whole slide is about, yeah, the pullback notation here. I hope this was clear. And then let's do some more, I would say, more or less obvious notation. So I use Einstein summation, and yeah, I have the short notation for the partial derivatives. So I don't write the fraction, just dx and so on, du. And yeah, there is this total derivative operator, which is the sum of these partial derivatives, and you have the specific coefficients in front. So basically what it does, it treats everything. So it treats u as a function u of x and so on, and then you just have the derivative with respect to x. So it imitates this differentiation with respect to x, but on the jet space, not on m. And yeah, then we have vector fields where we have these coefficients vi and v alpha, dxi, du alpha, and so on. And because we have a fiber bundle and we have some additional structure, so there are some additional properties of vector fields. So for example, there are the projectable vector fields. So this means there are some vector fields here. If this vi coefficient does not depend on u, then you can project this down to a vector field on m. This will be at some point a little bit important, but if you haven't seen it before, so it's not so really important at this point. And yeah, they are also called the so-called vertical vector fields. So this means when you project them down, then you always get 0. So this means that these vi coefficients do all vanish here, and you only have this v alpha coefficients. And yeah, then it's a little bit more notation. So when you have such a vector field on your space E, then you can lift it to a vector field on jke, formally writing it with such a jet of the vector field, and then you get some higher order partial derivatives. So basically you have two parts. So you have such a total derivative, and then you have such coefficients, characteristic coefficients, I call this, and derivatives of this characteristic coefficients. So the characteristic is given here. But yeah, this is only important if you're, let's say, an expert in this field. So, and yeah, then there's the characteristic vector field. And so I think that's it with the notation. So I hope this was understandable. So and now let's go back to what the talk is actually about. So here again is the statement. So if you have a PDE given by such a function f, such a zero set here of second order, and if it satisfies sufficiently many symmetries, I will specify this later, and conservation laws, then it must be variational. So yeah, variational means, roughly speaking, that you can write this Euler-Lagrange expression here, your f. Conservation law, maybe I should specify this a little bit more. So in the PDE case, it's roughly speaking a divergence expression. And I have an example here, so I don't know if I should go through this. Maybe I will do it quickly. So I hope that everyone knows Schrödinger's equation written here. Psi is the wave function, so the solution. So you can take the absolute value of psi, and you get this rho, this probability density. And then there's another thing you can compute here, this j, this vector j, which is the probability current. So everything depends on this wave function psi. And then this equation here will be satisfied on solutions of the Schrödinger equation. So this is a conservation law. So the current and the, yeah, I call it current conservation. So basically you construct such a vector capital J, which consists of rho, the probability density and the probability current. And then it's just a formal divergence of this J written here equals 0. Or you can also maybe write it with the total derivative if you want, since we introduced this notation already. So on solutions of the PDE, this will be satisfied this equation. So it's basically, you have a differential equation and you derive some other first order differential equation, and this is then called a conservation. And yeah, it has some physical interpretation, of course, but I will not go through this. So basically you consider here for the Schrödinger's equation, you introduce this t will also be considered as some coordinate like x on a manifold M. So let's call it x0 also. But this is just an example. And okay, symmetry, I think everyone knows how to handle symmetries somehow. So it's basically a Lie derivative of your differential expression, which must vanish. Then this is called a symmetry, but we have these additional terms, and I will also explain in my talk where these terms come from, why we have not only the Lie derivative, why there are also these additional terms. So yeah, so now in my talk I will make everything a little bit more precise and explain, for example, why we define the symmetry like this. And also will tell you more about conservation laws and variation. But before we do this, I will make a connection to Noether's theorem. So here is how you could formulate Noether's theorem. So if you have a differential equation f or such an expression, and if it is variational, then you have such an integral functional I. And if this integral functional is invariant, if you have symmetries, then you can prove that there must be also some kind of conservation laws. So this is usually the classical formulation of Noether's theorem, only in words. But there is a converse to this. So again, if you have a variational differential equation, and if you also have some kind of conservation laws, then you can also prove that your I must be invariant in some sense. So Noether, Emil Noether has also proven this direction. And what we want to do here in this talk is that when we have a differential equation, if it satisfies some symmetries and conservation laws, then we want to prove that there exists such an I, so that this is variation. And yeah, as you can see here, there show up different objects. So the differential equation and this I and so on. And here only you have the F's in formulation. And to get this a little bit more consistent, and what will also be very important from now on in my talk, is that we will not consider the differential equation itself, but we will consider a weak formulation of the differential equation. So what is a weak formulation? So basically you take a differential equation, you pull it back, and then you multiply it by some test functions, phi, and then you integrate over it, over some set omega, and set it equals 0. Then you get the weak formulation, which is denoted by this k here. And yeah, this will be very important in this talk. And then you can formulate everything with the k, basically. So equivalently, you don't need this f and this integral functional I here anymore. So you just, if you have this weak formulation k, and if you can define what it means that it is variational and what it means that k is invariant, and then you can also define what it means that k satisfies conservation laws. So, and this also holds for all the other directions here. So basically you can do everything with the k, and yeah, it will be important. Okay, so I think that's it for the connection to Noether's theorem. There is one more thing I want to add as a kind of note here. So you can also do a little bit more efficient notation maybe, or more advanced notation, if you neglect this integral sign here and the pullback by the section, and also the test function somehow, and just use a differential form, which is denoted by this delta. It's called source form. So you have only your f here, the differential equation expression. And then this test function here will be identified by this differential du alpha and then wedge dx, the volume form on M. So I think Floris Tarkins was the first who used this object in a paper written in 1977. I'm not exactly sure, but I think he was the first. And yeah, then you can do more, let's say, advanced calculations. But for the talk, I decided to formulate everything with the k. And I mean, there's a direct correspondence to this object, so it's basically the same, more or less, you could say. Yeah, and then one more. So for this test function phi here, this will basically be identified by a vertical vector field. So it's not just any test function, and I will explain this a little bit more now, since this will also be needed. So, and for this, maybe it's good to recall calculus of variations briefly. So yeah, we have a section here S, and then we do some kind of transformation or perturbation of the section. So we get a new section, but we do not allow any transformation. So the transformation is in such a way that we do not change the x coordinates. The transformation does only work on the u coordinates. And there's also no change at the boundary, so no perturbation at the boundary. This is formulated here in this complicated equation. And yeah, then you can compute the generator of this transformation. So this t has nothing to do with the t in the Schrödinger's equation, right? It's just a flow parameter. So you can compute the t derivatives at t equals 0, then you get the generator here, this vector field, and it will be a vertical vector field, and this part of this vector field will be in this set here, pi minus 1 omega, just because of these two conditions here. But this is a kind of technical thing, I would say at this point. Yeah, here's the expansion in t, not so important. And yeah, I wanted to tell you why our test functions will be identified by vertical vector fields. So if you now have such an integral functional and you do this perturbation. So you compute the first variation here, functional in the direction of v. So you can write it as a formal Lie derivative if you want, because of this here. Then you get this. Then you do the usual calculation. So applying the Lie derivative to the Lagrange function gives you this here. So partial derivative is respect to u of L. And then, yeah, you have here higher derivatives and also derivative of this component of the vector field. And then you do the usual trick. You do 1 times partial integration, right? There's no boundary term. It will vanish because we have support in this set. So at the boundary, everything vanishes, and then you get here the Euler-Lagrange expression. You can pull out the component of the vector field here. And yeah, then this will be just a differential equation f here. And here you have this vertical vector field. And then this is just a weak formulation, right? Here, your differential equation, here your test function, basically pull everything back. And so that's why we use test function as vertical vector field. Basically, it comes already directly in the calculus of variations, but we will also only allow such weak formulations which are possibly non-variational, but where we still have this specific test functions. So here is it again, everything what I said on the slide before. So also for non-variational weak formulations, we have the specific test functions here. And yeah, here this is the slide with all the kind of additional assumptions we have to make now for our PDEs. I mean, if you say, well, I can prove something that the PDE is variational, there's a very large, yeah, you can formulate PDEs in many different ways. So we need kind of more restriction for our PDE now. So the first thing is that test functions will be identified by vertical vector fields. And then, as you can see here, that your PDE has lower index and test function has upper index. So these are kind of contravariant objects, and they transform reverse to each other. So this is an additional property for our PDE now. So the transformation now for our differential equation is somehow fixed, which is an additional assumption. So this also implies that the PDE has as many components as our solution U has components. So if you have only one PDE, a scalar PDE, then we have a scalar solution, no vector valued solution, and so on. And also the ordering of the PDE is fixed. So if you have a system of PDEs, then you have a first equation, a second equation, and so on. So you cannot just simply change the order, because the first equation somehow corresponds to your first component of U and so on. And yeah, the symmetry is of course also, so I told you earlier that the symmetry will be defined in such a way, and it basically comes from this formulation or defining the symmetry of this weak formulation. That's why we have this expression. It's not so important at the moment, but you see. So in summary, you see that we have a little bit more assumptions on our PDE. This is basically what I want to tell you on this slide here. Okay, and I said that we can formulate everything with this K here. So the definition for variational now will be, so such a K or a weak formulation will be variational if there exists a functional I such that you can write it as formal Lie derivative of this I. And this holds for every section S and for every P vertical vector field V, and this V has support here in this set T minus 1 omega. So it's not a trivial definition. I have an example here, but it's not important. So this definition does not imply that all Ks are variational. There are also non-variational, for example, this here, but it's not important, right? I just want to show you that this is non-trivial definition here. Okay, so we have defined this, and now we have to define also symmetry for K and a conservation law for K. So this will need maybe some more slides, but before we come to this, I want to show you now the necessary and sufficient conditions, or let's say the integrability conditions, when this is satisfied, so when this K is variational. And it's actually pretty straightforward, I would say. So here it's the K again. Yeah, we ask ourselves, when can we write the K as such a Lie derivative here of some functional I? And to formulate these integrability conditions, first of all, you can apply again such a formal Lie derivative on such a K, because for a fixed V, this is just a functional I, right? I mean, then you consider F contracted with V as a Lagrange function, and then you of course know how to apply Lie derivatives, so we can do this. So, okay, here is an equation. So this equation is always satisfied for any integral functional I with Lagrange function. You interchange here the Lie derivatives. Here you have W and then V, and here you have V and then W, and then you also subtract the commutator, or the Lie derivative of the commutator. So this equation will be always satisfied. And yeah, this now gives us an idea how to define the necessary conditions for K. So basically we first plug in the vector field V in our K, and then if it would be variational, then we can write it as this expression, and then we end up here. We also plug the W into this K, and if it's variational, then we can write it in such a way, and we have here this line. So I hope it's clear. You can see it if you plug in the commutator in the K, and if K is variational, then we can write it as a Lie derivative with respect to this commutator. So this is a necessary condition for K to be variational. And it's also, it turns out that locally it will be sufficient. So yeah, with a kind of Poincare lemma, you can reconstruct your I by this formula. I mean, this formula is known. It's basically the same as for differential forms. Then yeah, you just compute your functional I here by this formula. And yeah, I want to make one more analog, because I think it's maybe the best way to understand this problem, because I think everyone knows how to handle or to work with differential forms. And here in the calculus of variation, it's almost the same. It's not exactly the same, but almost the same. So you have a zero functional instead of a zero form. So a zero form would be just a function. Then you have a one functional instead of a one form. Yeah, one functional because you can plug in one vector field. Then you have a two functional where you can plug in two vector fields and so on. So it's the same as for differential forms. And then you can define a kind of exterior derivative. So in the same way as for differential forms. So for functions or for zero functionals, you just define it as the Lie derivative of the functional or the first variation. And this delta here, yeah, this would be then definition. So if you define it for all vector fields with this additional assumption of being vertical and have support in pi minus 1 omega, then you get the definition of this operator. And yeah, also for one functionals, we can define such an exterior operator here by this formula. I think this is also known to people. So yeah, you first plug in the vector field and then you apply the Lie derivative and so on, and you have also the commutator involved here somehow. So it's exactly the same as for differential forms, for one forms, to define the exterior derivative. But the difference is that we will not define the operators for all vector fields, only for vertical vector fields and for vector fields which have support in this set. So this is a kind of the only difference here, and you should be careful with this. Yeah, then you get such operators. You can also define delta 3 and delta 4 and so on. with a similar formula here. It's getting a little bit more complicated, but you can write it down. And as an operator identity, you always get this equation here. So this will always be satisfied. And you also can construct such a sequence, actually a locally exact sequence. So here you have the set of 0 functionals. Here we have the set of 1 functionals and of 2 functionals. And then you define these maps here. Exterior derivative, let's say delta 1 and delta 2 and so on. And I think, yeah, this should be quite understandable, I hope at least. At least I like this idea to see it in that way. And so basically that's all I wanted to tell you for the calculus of variation. I think this is more or less all we need. There's only one more thing I want to present you here, and these are the so-called Helmholtz conditions. So when you write this out here, this condition, this integrability condition, or you can write it as delta 2, so this is the same, then you of course get some conditions for f. So I mean, yeah, you write this down for all the vector fields, and maybe you do partial integration and so on, and then you get some conditions for the f. And yeah, these conditions look complicated here. These are called the Helmholtz conditions. So they are for second order f. There are 3 different kinds of conditions, and basically, yeah, it's a alternating sum of partial derivatives. Also, some total derivatives are included here. And yeah, there are some integers c, I, j, but they are not important. They are 1 or 2 or something. It's not important at this point. So yeah, when you do this calculation, you can, I don't know if you have tried it, but then you can directly derive these conditions here. So it is actually not too hard. Yeah, I think that's the last thing I want to mention about this variational things. And now let me tell you a little bit more about the symmetry on one slide, so it's not so complicated. So let's make an analog again. So let's consider omega just a one form on some manifold n, not on m or e, just one form on some manifold. And then the question arises, how do we define the symmetry of one form? And the most obvious thing one could probably do, you define it in such a way, when the Lie derivative of some vector field v of omega vanishes, then this v will be a symmetry. I mean, v should not be equal to 0, but this is kind of clear. And yeah, this is a good definition for a symmetry. And yeah, here is an equivalent notation. So for all vector fields w, you get that this expression here must vanish. And you can also write it in such a way. I mean, you first apply the Lie derivative to omega, and then you plug in the w. So you can write it in such a way also if you want. And now you can change these two things. So you can first plug in the w and then apply the Lie derivative. But then
excuse me, what is w?
W is just another vector field.
Just a second. Okay. Thank you.
Yeah, thanks. So yeah, v is a vector field and w is just another vector field. So if you change these two things, then it's not exactly the same. Then you also have to add this term here. So you have to plug in the commutator of these two vector fields. Then this is the same. So these things are all equivalent. And yeah, I made this reformulation because it will be used later. So it's good to have it here. So a symmetry of K of our one functional now is a vector field. Okay, let's say a P projectable vector field not equal to 0, such that this expression here vanishes for this V for all sections and for all W's, but W is in this set. So W is vertical and has supporting P minus 1 omega. That is kind of the additional conditions we always have. But for the symmetry vector field, we do not have this condition. So for the symmetry, it should be P projectable. It does not have to be vertical. So, but then this is the definition of symmetry. And yeah, as I said, it's not a really strange definition. Also, pretty straightforward, I would say. Yeah, that's all for the symmetries. And now for the conservation laws, or for the conserved current. I need to explain you a little bit more. So yeah, I told you at the beginning that the conservation law or conserved current is basically a divergence expression which will vanish on solutions of the PDE. And we also had an example. We had an example in the ODE case, this energy conservation. And for Schrödinger's equation, we also had an example. So let me repeat this ODE case once again. So when we have an ODE, so when n is equal 1, so then we only have one term here. Then this must vanish on solutions, the differential equation, then we integrate this, and then we get that J1 is a constant on solution, right? This was this energy conservation on the second slide. Or you could also say you have a first integral in this case, but for PDEs, it's a little bit different. There you really have this whole expression. Okay. So when you have something, such a divergence expression, which has to vanish on solutions of your equation, then I want to convince you somehow that you can write it in such a way. So if something here must vanish whenever f vanishes, then you can write it by some factor q and then times f. So maybe you need some weak conditions for this. I will not go into detail here, but we just say that this is the case now, right? That our divergence expression is q, some factor, and then Einstein summation with the f. So, and yeah, I hope it makes sense for you somehow. So, and if you accept this here, then you see, yeah, that q maybe can be identified with the components of a, let's say, generalized vector field. Because, yeah, you have here this Einstein summation and co and contravariant objects. And yeah, also you can look at the Noether's theorem, what it is there, and this q will be exactly this characteristic component of the vector field. So in Noether's theorem, this characteristic comes from a symmetry, of course. And yeah, here you can see how it exactly looks like. And we want to do something similar. But we allow a little bit more general factor q's. Or you could also say maybe q is an integrating factor if you want this. So let's now come to the definition for conservation laws of k. So if you find such a q, such a factor q, integrating factor, or whatever you want to call it, then you plug it into your k. So we consider it as a vector field, so we can plug it into a k, or as a generalized vector field. Then we contract it here with the f. Then we know that this is the divergence expression here. And then we can apply Gauss theorem or divergence theorem here. We can integrate. So instead of integrating over omega, we integrate over the boundary of omega. And we have here the unit normal vector and here the surface volume form. So we can write it in this way. And here you can see that this expression only depends on points on the boundary, right? That's why I wrote here. Everything is restricted on the boundary. So any section you will plug in here, things will not change, but on the boundary maybe it will change, but nothing changes inside. So if you have a section which does only change inside, but not at the boundary, so nothing will change at all. So this is basically, yeah, then our definition. So any generalized vector field Q, when you plug it into this K, and if this thing here only depends on the boundary of omega, then we call this Q a generator for a conserved current. So this is this. I hope this was understandable. Yeah, here is the same definition again. And this definition also makes sense. It's not a trivial definition or so. So the definition also holds for non-variational case. And this can be quite general Qs. They do not have to look like characteristic as a Noether theorem. And yeah, there's one more implication I want to tell you here. So for a fixed Q, so when you contract this Q with your F here, then you can consider this just as some Lagrange function L, what I wrote here. So for fixed Q, then you only can change the S. So this is basically a zero functional then for S. So and this functional will only depend on the boundary of omega. So it's basically a trivial zero functional. So which means that variations of this functional are always zero, or yeah, they don't change the functional. Because at the boundary there are no variations and everything only depends on the boundary. So this definition implies that the Lie derivative of this thing here vanishes for all sections and for all p vertical v with support in this set here. So yeah, this is kind of also important here. And now I come to Tarkin's problem, or this theorem, what we want to prove. Tarkin was the first who formulated this and also has proven this. So here are all definitions together. So this was the definition of variational here. And you can write k as such a Lie derivative of some I. Then this was an implication, or let's say a definition, an equivalent definition of conserved current. If this always vanishes, if you can find a Q, there exists a Q not equal to zero, such that this will always vanish for all vector fields with this property, then it's a conserved current or conservation law. And a symmetry was a vector field V, a projectable, such that this equation here holds. And I hope I motivated all of these definitions here sufficiently enough that you can live with this now. Yeah, so these are our definitions. And now we come to this integrability condition again. So this delta 2 was kind of the exterior derivative for our one functional k. And it was defined in such a way, was this expression. And now when we have a conserved current, so if this V is a generator of a conserved current, then this thing here must vanish for all W with this property of being vertical and so on. And then also if V at the same time is a symmetry, so if this whole thing here vanishes, then this thing here vanishes, right? So both things vanish, and so this implies that delta 2k equal to 0. And now we have to be careful for what kind of vector fields here. So for all the symmetry vector fields V, which is written here, and for all W, which are vertical and which have support in pi minus 1 omega. So by assumption of symmetry and conservation laws, you get the blue line here. But what we actually need to show that this is variational is that this thing here vanishes for all vector fields, not only for the symmetries, or for all vector fields, that this implies the red one. This also vanishes for all vector fields which are vertical and have support in p minus 1 omega. So the big question is now, can we go from the blue one to the red one? And this is basically the proof what has to be done. Everything else directly follows by our assumptions and additional assumptions we make in our theorem if you formulate it precisely. So, and here is the precise formulation. So here, yeah, again, we want to get from the blue to the red one, and here, yeah, the precise formulation. So I repeat it once more. So you have such a fiber bundle. What you need to be able to formulate a differential equation and so on. So you have this fiber bundle of basically any dimension you want. So the base dimension is arbitrary and also the fiber dimension is arbitrary. And you have a second order one functional. So here we strict to a second order. And then we have sufficiently many symmetries.
Sorry, what means one functional? One functional.
What it is?
What means the sentence one functional? What it means?
Yeah, one functional means that you can plug in a vector field and you get a number when you plug it in. Basically the same as for a one form. You can plug in a vector field into a one form and then you get a number.
So functional on vector fields?
Sorry?
One functional, it is a functional on vector fields.
Yeah, it also depends on a point. So a one form, you can plug in a vector field, but can also evaluate the thing on different points. So then you get some functions depending on points on your manifold. And for the one functional, it's basically the same. You can plug in a vector field, but then you evaluate everything on some specific section. So the evaluation on the section is basically in the analog for differential forms that you.
But one functional may be not differential, not one form.
One functional probably covariant, vector field contravariant, and this covariant, probably this one.
I don't understand what is it one functional.
It's true, I did not really give you a definition for this, but it always was such an expression, right? You have an integral, and then you have a function f, and then you can construct it with the vector. Then you integrate over x and some omega. So you could also write the omega here on this case. So basically, yeah, the k can be directly identified with the f. Everything else is fixed. So it's fixed, for example, that we have an integral. It's fixed that we pull back this whole thing by a section. So we also have the section here. And then, this will be contracted and then this will be integrated. So, it's basically like a one form, right? Omega, you can plug in a vector field. Then for a fixed point, you get just a number, but then you can vary the points. So the points of the vector field such that you get a vector on some point of your tangent space, and then you have just a function at the end, depending on different points of your manifold. And this thing here depends on different sections, so of your fiber bundle.
But essentially, the result of the one functional will be a number, right?
It will be a number, yes.
Okay.
So this gives you a number here. Okay, so then, thanks for the question. And I will continue with this theorem here. So we have sufficiently many symmetries now. One symmetry vector field usually is not enough. So sufficiently many means it's a kind of technical thing here that we can span the whole tangent space of E with all of our symmetry vector fields. This is not a completely trivial condition because we cannot span the tangent space of the jet space J to E, only the tangent space of E. So it's actually not so large as it might look like here. And then the second assumption is the conservation law or current conservation assumption, so that the symmetry vector field at the same time must be a generator of a conservation law. And if you have these two assumptions, then K must be locally variational. So this is the statement. I don't know if there are any more questions about this now. It looks a little bit technically, but yeah, so I think so far I didn't tell too much new things. I mean, this theorem is relatively new. I proved it in 2018. I will now show you a little bit how to prove it. But I think all what I did before in my talk, it was more or less basics, or I recalled what is known. And yeah, here is a table. So as I said, I have proven this in my PhD thesis in 2018 here. And I already told you that Tarkins was the first one who formulated the problem, who also did some great work on defining objects and so on, and for example, defining the source form. And he has also proven 3 different theorems. That's why I didn't write it out here in this table. And then Ian Anderson from United States and Juha Pohjanpelto, also from United States, have made a whole project out of this Tarkins paper, and they have proven different theorems with different assumptions. So the first one was in 1994. There they considered scalar equations, so that's why m is equal 1. So no systems, only one equation, but a PDE, so for any n of second order. And then they had shown with a similar formulation that if you have this span condition, which is different from mine, then your scalar PDE must be variation. And then Juha generalized this 1 year later. There he already considered systems where n is equal to m, but only of first order, and also only for very special symmetries for translations in x direction. Yeah, and then generally 1 year later, then they even generalized this here. So they proved it for second order, but then they had to use an additional symmetry condition. So again, translations, but also gauge invariance. And I mean, gauge invariance in translations is very special. I mean, translations is an abelian symmetry group, which is in some sense easy to handle, and gauge invariance is also special because it's an infinite dimensional symmetry group, and it's very large and has strong implications and so on. And yeah, then they did other things. So maybe what's important to notice here is that this theorem here, what I have proven here, generalizes these cases somehow, that we do not need the special assumptions of the special symmetries and so on. So this is actually not important. We only need the span condition, and this is also always satisfied in all of these cases here. Yeah, so, and I also have proven another theorem for fourth order, but only for scalar ODEs, so very special and a little bit different. I will not talk about this here, so only about this. And now we can come to the proof. I know it's late and I have already told you a lot of things, but I will now try to show you the main steps in the proof. And yeah, the proof is mainly be done in local coordinates. So sorry for this. This will get a little bit more technically now. So yeah, by assumptions, we have that this here must vanish, delta 2 of k, for all symmetry vector fields V and for all W in this set. And you can write it out here without integral and so on, then you get this equation. Maybe you do some kind of partial integration and things like this, and then you will end up with this equation. Here we have the different kind of Helmholtz expressions which you have for second order F. So there are the 3 Helmholtz expressions. And then you have the characteristic coefficients of the symmetries and also total derivatives of this characteristic coefficient. And the question is now, can we derive from this equation that the Helmholtz expression here almost vanished. Then you know that this is variation. Basically, we have to solve this equation here, which is another differential equation in some sense. And I wrote the whole system down here. So here is this equation again, what you can see here. And then I wrote down what H means. So there's three kind of different Helmholtz expression. I told you this is this alternating sum of partial derivatives and so on. So how it exactly looks like is not so important, but you have these three different expressions here. And the characteristic was this. So here you can see the vector field components involved. And we have several of these equations, let's say, because we have it for different symmetries. So this should be a symmetry vector field here. So yeah, this whole thing here, this is basically what we want to solve now. And here it is written again. So nothing basically changed, but what I want to present to you now is that I set n equal to 1. So there's only one x coordinate. So it's basically a case of ODEs, because otherwise it's getting even more technical. So u is still be vector valued, and there's only one x coordinate. And then this contractions with the index I and j simplifies a little bit. So I can always write x here, because there's only one. So there's only x1, right? So I just write everywhere where there's an index I and j, I write x, and also these coefficients vanish here. They are all 1 in this case. So it simplifies a little bit. So we have to solve this system. Okay, and then I need one more notation, the last one, but it's very easy to understand. So you have a function g defined on the first order chat. Then I simply write this is a first order function, because they only show up first order coordinates, not higher order. So it's not Landau notation, this O, it's just a notation for order of differential expression. So here you have second order coordinates involved. So then I would just short write g is the second order function, and so on. And also for higher order. Yeah, here's this characteristic coefficient, and then we also have this total derivatives on the characteristics. And you can now apply it, and then you get that this is a first order function, which is unimportant. And then this is the second order part. And you can do it once more. So you apply the total derivative here again, then you get this second order function somehow, which is not important exactly, and this specific third order expression. And now we plug in everything into our system. So we simplify it a little bit by writing some order notation, and then some of the things here will get a little bit easier. So this is one thing we will do. Another thing is that we use this purple here, this span condition. So we have actually several of these equations because we have several symmetry vector fields. And for every symmetry vector field, we get such an equation. And then we can add and subtract this equation, or doing in general linear combinations of all these equations, doing some kind of linear algebra, and then we get a new system. And this is written here. So when using this purple condition, this span condition, then we get this system here, these two equations here. And these two equations will now replace this equation. So I mean, I cannot write it out how to do exactly how this linear combination works. It's too complicated for the talk, not complicated in general, but you see it, there's already a lot of things on the slides. So, but it's an easy step, it's the first step. So you use the span condition and then you reformulate it a little bit. You can do it. You cannot do so much algebra that you immediately can derive that the Helmholtz expression vanishes. That's not possible, but at least a part of it you can simplify. So I will not write the span condition anymore because we already used it. So we have now here our transformed system. And we go now to the second step. So the second step is now we cannot do any more linear algebra. we have to consider the different kind of orders in our system here. So, and the highest order comes from this first Helmholtz expression, because we have here double total derivatives applied to f. So f is of second order. So let me also briefly mention that this comma u alpha xx means partial derivative with respect to u alpha xx. But I mean, this is still a second order expression here. And if you apply two total derivatives in a row, then you get a fourth order expression. This will be a third order expression, and this will be second order. So this whole thing here will be third order. And here somehow you get the fourth order of this specific form. All other things are not important. This will generate a third order and this second order. So this whole middle Helmholtz expression is of third order, and the last one here is of second order. So then when we have here fourth order, we know that this fourth order term cannot cancel with these kind of terms, because this is first order, this is third order here, this is second order, and this is second order. So this whole thing here is third order, but here there is fourth order, which cannot cancel with these terms, so they must vanish separately. So this thing here must vanish separately on the whole jet space, because this equation holds on the whole jet space. So, and then this forces that this equation must be satisfied. So f beta u alpha xx u gamma xx equals 0. So I told you that these are two partial derivatives, and you can integrate this easily, and this gives you that f must be affine linear in second order derivative coordinates. So some coefficients a beta and b beta, and then here affine linear, and this is first order. So this is what you derive in the second step of the proof. And then basically it's more or less always the same. You do such a kind of order discussion in some sense. So I don't know if I have to go precisely to everything now. So we already derived in the second step that this f alpha is affine linear in this way. And we can now plug it into the Helmholtz expression again in all three of them and compute them again with this new information here. And then we will find out that they look like this. So this is not of fourth order anymore, it's of third order, but with this specific coefficients. And then there are some unimportant second order terms. And this has some unimportant first order and this specific second order and so on. And yeah, then you have this form, plug it into your equation here and look precisely at the third order expressions. I did this here, which again must vanish separately here, for example, because then this is only second order, this is first order, this is already zero order and so on. So this must vanish separately again, the third order, and you get new conditions and you plug it in again and again, and I think I will not go through the details. So you do this many times, and as you can see, these are getting lower and lower order, and finally at some point you will derive that everything must be zero after several steps. So in the ODE case, as I have discussed it here, it's actually not so hard to do this. In the PDE case, it's really not easy to do this, even if you only have to look, let's say, at the fourth order and look at it that something must vanish. There, it's really complicated, and yeah, so it's the proof is not trivial at all, I would say. But okay, I hope you got an idea how to do this, and I think it doesn't make sense to talk about the details here anymore, or I don't know, maybe I can. So basically I told you everything I wanted to tell you here, and now if you have questions, then maybe I can answer some of them. So thank you very much for the attention, And yeah, it's already late, so thanks that there are still people here. And yeah, if you have questions, then please ask me.
Well, thank you very much. Questions, remarks? Well, I have a question and I have a remark. The question is, well, I didn't understand. Do you have a proof for PDEs or not?
Yes, I didn't. I have a proof for PDEs. There's also an article on arXiv where I have where this proof is written. So here I only showed you the ODE proof, but there I have an PDE proof.
You have a proof for arbitrary PDEs of second order, yes? Or no?
Arbitrary in the sense that, you know, I have this additional assumptions what I showed you on some slides. So, for example, that the system of PDEs must have as many components as you have, as the fiber dimension is, and so on. So, yeah, I mean, yeah. So I have a proof for systems of PDEs of second order, but there are some additional conditions initially for the PDE. Should I repeat this or?
No, I just, well, if you send me a reference, it would be okay, because it's late already.
Yeah, I mean, I have this paper. You can find it on arXiv with my name, Markus Dafinger.
Okay, I'll find. Which year?
Sorry?
Which year?
I think it was 2018, yeah, 2018.
Okay. And a remark is that, to my opinion, it is a bit unfair discussing invariant formulation of Lagrangian formalism in less problems, Noether theorems, not to mention works by Alexander Vinograd.
Yeah, that's, I mean, I didn't, there are many people, also Dimitar Krupa and so on, I didn't mention here, I only mentioned Tarkans here. And of course, yeah, I mean, he is also very famous in this field. I know that he works in Moscow.
He worked in Moscow, yes. Otherwise, the reference would be incomplete. Okay, more questions, more remarks.
Yes, I also have a small question about you use a weak formulation of differential equation. And does it mean, for example, symmetries of this weak formulation are equivalent to symmetries of differential equation in standard sense?
No, they're not equivalent. So it's a little bit different, yeah. I mean, for translation symmetries, it's completely equivalent, but if you have non-abelian symmetry groups, then they are indeed different. So this is a kind of a, yeah, problem or negative point, you could say, maybe of the theorem that, yeah, that is not symmetry in the usual sense, but it's also the question what means the symmetry in the usual sense. I think there is not only one definition of symmetry of a PDE which everyone would completely accept. It's even hard to define what it means to have a differential equation, I would say, but yeah.
But at least for classical symmetries, so transformation of jet space which preserve equation takes solution to solutions.
Yeah, that's a good definition, yeah. But I mean, for example, if you have, let's say, an equation, I don't know if I can write here, is it possible? If you have the equation u(xx) equals 0, So then it has the symmetry dx, so it does not explicitly depend on x. But you can now equivalently write this equation as e to the power x. It has the same solutions times ux, uxx, right? Just by multiplying it by some factor which does not vanish, which vanishes nowhere. So
Yes.
it's now equivalent to this,
Yes.
but maybe the symmetry will change.
No. It's a problem of coordinates. If you take a geometrical object, the result will be the same.
Yeah.
Of course,
So,
if you use coordinates, everything becomes fuzzy. But forget about coordinates, and the symmetry algebra for these two equations will be the same.
No, it's not coordinates. That's a factor, right? So he talks about operator or equations. So for equations, symmetries are the same.
Yes, but we are speaking about equations, not operators.
Yes, that's important. That when we want to talk inverse calculus for equations, not operators.
Yeah. We did not hear anything about symmetries of operators. They were symmetries of equations. So there is no difference.
I think the definition what you gave me before, that if solutions are mapped to solutions, is fine. But my definition is a little bit different from this. So this is maybe, yeah, a little bit negative point of this theorem, but I haven't fixed this problem so far. So maybe it can be fixed in the future. I don't know. Maybe not.
Okay, thank you.
More questions? More remarks? Well, thank you very much again, and we meet in 2 weeks. Thanks.
Okay, thank you very much.
Have a good night.
Yeah, good night.
Спасибо, до свидания.